Okay, I'm going to be going through the solution of the final Hardy-Weinberg practice problem. So the initial question asks if the population were in Hardy-Weinberg equilibrium, what would be the genotype frequencies in the next generation, and what would the allele frequencies be? So I like to start off by just writing down what I know about my initial population, and that is that the frequency of the dominant allele A is 0.7, and the frequency of the recessive allele, little a, is 0.3. So to determine what the genotype frequencies would be for the next generation, we use the Hardy-Weinberg equation, which says that the genotype big A is p squared, which in this case would be equal to 0.49. And the frequency of the heterozygous genotype, big A little a, would be 2pq, which in this case is equal to 0.42. And finally, the genotype little a is q squared, 0.3 times 0.3, which is 0.09. To determine the allele frequencies from these genotype frequencies, remember that 100% of the gametes produced by organisms that are big A in genotype will also be big A, and only half of the gametes produced by heterozygous organisms will be big A. So the frequency of the allele P is 100% of the frequency of organisms that have the genotype big A, and then half of the heterozygous genotype frequency. And the same goes for the frequency of little a, which will be 100% the frequency of organisms that are little a, and half of the heterozygous frequency. You can see that both the genotype frequencies and the allele frequencies are staying the same from generation to generation, and that confirms that this population is in Hardy-Weinberg equilibrium. So now we want to look at the situation in which there is differential fitness between the genotypes and how that affects the genotype frequencies and the allele frequencies from generation to generation. So in this case, the survival rate of organisms that are born big A, little a, and little a is 0.25, 0.10, and 1. So in our first generation after the initial population, we can start by calculating the genotype frequencies using the Hardy-Weinberg equation in the same way that we did in the population that was in Hardy-Weinberg equilibrium. So again, we have the frequency of big A being 0.49, the frequency of big A being 0.42, and the frequency of little a as 0.09. So now we want to ask how many of these zygotes will survive into adulthood, and we can answer that question using the survival rates we were given. So we know that only 25% of zygotes that are big A will survive. 10% of zygotes that are heterozygous will survive. And 100% of zygotes that are homozygous recessive will survive. So what is the implication then? If we imagine that there are 100 individuals in this generation, this means that only 12 organisms that are big A have survived into adulthood, rounding down from 12.25. only 4 heterozygous organisms have survived and 9 homozygous recessive. So in calculating the allele frequencies, again, remember that 100% of the organisms that are big A that survive into adulthood will produce a big A gamete, and only half of those that are heterozygous will produce a big A gamete. And to get that into a frequency, divide that by the number of organisms that survive into adulthood in total. So the frequency of the dominant allele is 0.56. Using the same reasoning, the frequency of the recessive allele is 0.44. And you can see that from the initial population at time t equals 0 to the next generation, time t equals 1, the allele frequencies have changed, and therefore we can confirm that this population is not in Hardy-Weinberg equilibrium. So now, in order to definitively answer whether this population is becoming more or less diverse over time, we want to calculate the genotype and allele frequencies in the next 2 generations given the same survival rates. And so let's see what that looks like. In our generation t equals 2, we can use the Hardy-Weinberg equation to calculate the genotype frequencies using the allele frequencies that we calculated in the previous problem. So the frequency of zygotes that are big A will be p squared, which is 0.3136. The frequency of zygotes that are heterozygous will be 2pq. Which is 0.4928. And lastly, the frequency of zygotes that are a is q squared, which is 0.1936. Again, we have to apply our survival rates and ask how many of these zygotes will survive into adulthood. So given that the same survival rates apply in this generation as they did in the previous generation, we can calculate the number of organisms that survive into adulthood in the same way. Again, it's easier to see this concept if you assume that 100 organisms are born in this generation, or rather 100 zygotes are produced. So our calculations tell us that only 7 big A zygotes will become adults, 4 heterozygous zygotes will become adults, and 19 homozygous recessive zygotes will grow into adulthood. we can calculate our allele frequencies in the same way. And we see this time that 0.3 is the allele frequency for the dominant allele, and 0.7 is that of the recessive allele. Just to confirm, the change in allele frequencies, the trend given these survival rates, we'll calculate genotype and allele frequencies for generation t equals 3. And we can see already that the number of organisms that are homozygous recessive greatly outnumber the number of organisms that are either heterozygous or homozygous dominant, which confirms the trend that the frequency of the dominant allele is greatly decreasing, whereas the frequency of the recessive allele is significantly increasing. So in answering whether or not this population is becoming more or less diverse, we see that one allele is heading towards fixation, and that means that this population is definitely becoming less diverse. In asking what type of selection might be acting on this population, it's useful to consider which genotypes are more fit than others, and we can answer that looking at our survival rates. So 25% of big A zygotes survive, 100% of little a zygotes survive. However, only 10% of heterozygote zygotes survive into adulthood. So the fitness of the homozygotes is significantly greater than that of the heterozygotes, suggesting that underdominance is the type of selection at play. Thank you for listening.